matter is going to tend to slow the expansion down. That slowing the expansion down might be kind of moderate, like the green curve, in which case the universe will slow, 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 but will probably continue to expand forever. If there's a lot of material in the universe, though, that slowing down, the decelerating the universe, might be quite extreme. And sometime, probably in the distant, but maybe not infinitely distant future, the expansion of the universe will slow to the point where it will stop and will start coming back down on itself. Now, the expanding universe implies that some billions of years ago, our current estimate is about 14 billion years ago, the universe started at a time when everything was hot and dense. This is a phenomenon we call the Big Bang. If the universe slows and stops and then recollapses, it could be that we have at the end of time what we call the reverse of the Big Bang, or we actually do call it the Gnab-Gib, which is Big Bang spelled backwards. So if we think about the universe, wouldn't it be nice to know what kind of universe we live in? One which eventually will expand and become cold and dim and sort of a cold death, or one which will have this great fiery ending? Which sort of universe do we live in? And the key to understanding this is how much matter is there in the universe, the density of gravitating matter in the universe. So let's go on out and start counting matter in the universe, see how much we've got. Now, in this room, we live in a very dense place in the universe. We have a lot of people, we have a lot of mass in the Earth and the solar system, but most of the space is empty. And so what we want to do is to find a piece of the universe which is sort of representative of the whole universe at once. We want to find the biggest thing which has gravity in it, but really could be representative of the big universe, the whole universe. And so we look at galaxy clusters, which are the largest things in the universe, which are actually held together by the gravity of whatever is inside the galaxy cluster. So the first thing we can do is we can go and count galaxies. 1, 2, 3, 4. I do this. 1, 2, 3, 4, 5, 6, 7. And you figure out how much mass would be in all the gas and stars of the galaxies, and you add it up, and you get a very small number, nowhere near enough to close the universe, to bring it back on itself. And so you could stop there and say the universe is going to expand forever, except for one thing you might want to remember, which is that if you only look for the things you see, you might miss the things that you can't see. It turns out that most of the mass in the universe is completely invisible. Let me give you an idea of how, though, we can see it. We use a trick that Einstein showed us, that if matter can curve space, then anything going through that space is going to curve. So if you can imagine even invisible matter sitting in a big lump in space, light passing through that zone is going to be curved. It's going to act like a lens. And so even if we can't see the matter, we can see the effect of it by looking at how it lenses or distorts the images of things in the background. So I want to show you what happens when we have a piece of invisible matter, of dark matter, that floats across an image of Baltimore Harbor, as it turns out. Baltimore, by the way, is where the Hubble Space Telescope is operated from. Can you see the dark matter? You can't see the matter itself, it's invisible, but can you see the effect, the distortion of the background that you see when the dark matter goes across the picture? So this is what we look for in the universe, looking for the distortion of matter. In this next version, you'll see a galaxy background. And we'll see that same piece of dark matter go in front of the galaxies. Take a look and see how the galaxy shapes are changed as the dark matter goes in front of it. It's quite beautiful. You see they're elongating these lovely arcs. Sometimes they have little bits that pass around in front of it. We look for patterns just like these in galaxy clusters and throughout the universe to see how much dark matter there is in these galaxy clusters. So this is one of my images from the Hubble Space Telescope. This is a galaxy cluster called the Beast because it has such extreme gravitational lensing in it. You can see that this is a single galaxy that's been twisted and pulled into an arc. Here's a second galaxy pulled into a different arc, and a red galaxy down here into a third arc. We use this distortion to measure how much invisible matter there is in the clusters, and from there we extrapolate to the rest of the universe. So this is one of the ways we can see the dark universe. Even though we can't see the matter that seems to be in these clusters, we can tell it's there. What we find is that if we compare the matter that we see from the distortions with how many stars and atoms and regular stuff we see in there, we find that most of the mass of the universe cannot be normal atoms. It is truly invisible. Very likely, it's some sort of subatomic particle, something that interacts very, very weakly with normal matter, but has just enough mass, and there's just enough of it floating through the vastness of space that it is enough to create the distortions we see. So we call this dark matter, and as yet, I can't tell you what sort of particle it is, what sort of thing it is. It is still a mystery. But we know there's a lot of it, about 6 times as much dark matter as normal matter. Is it enough? What's the universe going to do? Well, the total mass that we find in dark matter is tantalizingly close, but not there. 25% of what is needed to pull the universe back on itself. So at this point, we can say, well, maybe the universe will expand forever. This is work that I was doing in the late 1990s with my colleagues, looking for dark matter in these clusters, doing inventories of the universe. And we were just about patting ourselves on the back, saying, we solved cosmology. We know what the universe will do. Right about the same time, right at the turn of the millennium, however, we got some surprises. And these surprises came from looking at a type of exploding star we call supernovae. Now, I don't have time to tell you a whole lot about supernovae. Astronomers love them because they're really big explosions, and we love explosions. Some of them are required in order to make all of the atoms that make up our bones and blood and our planet. That's always nice as well. But the ones that cosmologists like are ones that we can use as maps, as pointers to different parts of the universe to allow us to map out what the universe is doing. They're very bright, and we can see them to great distances and see them very long ago. And what the supernova experiments found was that none of those curves I just showed you seemed to fit the data. What they found is that the supernova were always sort of kicked a little bit above even our curves where the universe never slows down at all. It looks as though the universe is actually swooping upwards in acceleration. This is weird. This is really weird because there is nothing in the universe we know that could accelerate expansion. Gravity pulls. Gravity doesn't push. There's something in the universe that's acting like anti-gravity. We discovered it less than 10 years ago, and we still don't know what it is. We call it, for lack of anything better, dark energy. Now, I've been working on dark matter. When I saw this result, I said, the supernova people, they must be wrong. There's nothing that can act as as anti-gravity. It does not exist. It is not in the laws of physics. And so I was very skeptical about this, and I hope you are too for another minute or two. It turned out that we needed a little bit more evidence in order to figure this out. And this came from one more set of beautiful experiments that were done a few years ago, looking at remnant radiation, just a little bit of light left over from the Big Bang. This light was actually a microwave signal that was discovered way back in the 1960s, for me, way back in the 1960s, that is really a little bit of leftover heat, a little bit of leftover light from the very intense conditions just after the Big Bang. We see this coming to us all over the sky. That oval is a projection of the sky all around us, all directions it's coming from us. And we think that this gives us an idea of what the universe was like in very early times. Now, when we think about what the universe might be like, we actually expect to see a characteristic ripple. It's not completely smooth. It's got a little bit of flow, a little ripple to it, very much like what happens when you have water or air blowing over sand. You see there's a ripple there? There's a characteristic size of that ripple. You can sort of get a feel for it. They're not all exactly that size. It's not like a dot pattern, but it's sort of a rough idea that this is what the size of these things should be. When we take a look at the cosmic microwave background and the size of the ripples that we see in that map above, what we find is that we see the ripples. They're of about the right size. And the last thing we have to do to understand that is to see whether the light passing through, that light has been going for nearly 14 billion years before it falls down our telescopes, whether the light going through all that space has gone through an overall universe that is flat space or curved space. What will happen is that depending on what sort of space we have, flat, curved this way, or curved that way, it'll tend to magnify or demagnify the pattern. What was found with the cosmic microwave background was that the patterns were exactly what we expected, to like incredibly, excruciatingly great detail with a flat universe. Now this made everyone just absolutely fall down in shock because the amount of dark matter there is in the universe was not enough to keep the universe flat. In order to keep the universe flat, you needed about 4 times as much dark matter, 4 times as much matter or energy in the universe to make space snap flat. About 4 times as much, huh? So what happened is that the dark matter, the cosmic microwave background, and the supernovae experiments, all 3 of them being mysteries, they converged to give us a really new way of looking at the universe. This is a plot that shows how much dark matter there is in the universe, from 0 to a lot, and how much dark energy, that anti-gravity, the accelerating thing, on on the other axis. And what we found